Hello everyone, welcome to the channel. I'm Saptarshi Mukherjee. I'm a software engineer 3 at Google and I've been a competitive programmer. I've had some good achievements on some good platforms like ACM-ICPC and Facebook or Meta Hacker Cup, and I've been a master at Codeforces 6-star at Codechef. I'm a BTech honors graduate from IIT Bhilai in CSE discipline, and I've been a former member of National Blockchain Project at IIT Kanpur and an author at some publications of edge computing, some other fields. So yeah, that's a brief intro about myself. In this um, in this video, I'm going to discuss the last two most difficult two problems of Codeforces round 927 using tourist solutions. I won't be discussing the last problem in the best detail. The second last problem I'll try to cover the most of it, but last problem I'll try to give you a summary of some parts, and some parts probably you have to learn yourself and then complete the pieces. But anyway, we will see how tourist has solved them, what we can learn from his solutions, and we will get a glimpse of how to really attempt through many of these problems. Actually, from two problems it would give us very faint idea, but by looking at many problems, how tourist actually solves such problems, we can get the idea of how we can ourselves attempt those problems. So these are the great programmers. You have tourist, whose solutions I'll be using for this video. He is a legendary grandmaster. The actual name, Gennady Korotkevich, is from Belarus, from ITMO University. So the graph tells a lot. This is the one of the best things for me, that he has been coding since 2010, and now it's 2024, so it has been 14 years, and you can still see the consistency over here. That's Gennady Korotkevich to me. That's the reason I choose him, even at this time when we have so many other people over here. So his best was 3979, and I'm hoping we'll see him back once again in some time there. So in these sessions, we are going to look at his solutions, try to learn some things. We are going to look at some maybe complex concepts that come up during the questions, during the problems that we solve, and we'll try to tally it with tourist solutions, try to learn some things that he has done differently, etc. Yeah, the attempt is not to compare. The attempt is definitely not to say that, okay, this is what I've understood about tourist. This is definitely not to make a judgment about this great program. It is just with a learning intention. His consistency says a lot, and it will take us probably 14 years to actually understand what he has done in these 14 years. I'll definitely not make such false claims, but I'll hope that these discussions will bring us something, will tell us what tourist is so good and what are the good things we can find from this program. So let us see. We'll start with this problem, feed cats. There is a fun game where you need to feed cats that come and go. The level of the game consists of n steps. There are m cats. The cat I is present in steps from Li to Ri, inclusive. In each step, you can feed all the cats that are currently present or do nothing. If you feed the cat more than once, it will overeat and you will immediately lose the game. Your goal is to feed as many cats as possible without causing any cat to overeat. So a cat should not eat more than once. And now you have to find the maximum number of cats you can feed. You need to select several integer points from the segment from 1 to n. So you have to select some points. At each point you are going to put the food. Whatever cats belong in that point, whatever cats cover that point, they all will eat that food. Now this is actually the formal version of the problem. You need to select several integer points from the segment in such a way that among given segments, none covers 2 or more of the selected points, and as many segments as possible cover one of the selected points. You don't have to minimize the number of selected points, you have to maximize the number of cats being fed. But you have to ensure that no cat is actually eating from 2 different points. That is, in the range of a cat, more than 1 point should not be selected. So let us see. The example and this explanation will actually make it clear. So if you look at this 15.6, So from 1 to 15 we have these steps. We can draw a number line to understand this. 1, 2, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. Now over here 6, there are basically 6 ranges: 2 to 10, 3 to 5, 2 to 4, 2 to 10, 3 to 5, 2 to 4, 7, 7, 8, 12, 11, 11. 7, 7, 8, 12 and 11, 11, right? Yeah. These are my positions. If I have to cover them, what should I do? I don't have to cover all the cats. There are 6 cats. If I choose these two, what is the problem? Then this cat and this cat will basically get 2 places, will get food in 2 places. That is not what I want. I should never have that case. So I will choose less points if necessary, but I'll not choose more than 1 point for a certain cat. These these brackets are cats. Okay, so now I can say, okay, we can choose this one. This will cover this cat, and this cat. 3 cats are covered. I cannot choose this one because though this cat is remaining, but this one will not like it. This cat will die if I choose that one. So I'll not choose that one. I'll proceed here. I'll say, okay, for these 2 cats, these are my common places, these 2 cats. I can't choose up to here because the red cat is going to be unhappy. So these 2, out of these 2, I can choose any one of them or both. Okay, I can't choose both of them because then this cat will be unhappy. So I can choose any one of them. I can choose this one. So with these 2 cats, what can I cover? I can cover this. With these 2 points, I can cover this cat, this cat, this cat, this cat, and this cat. With these 2 points that I have marked in yellow. So which one am I leaving? I cannot cover this one, but I don't worry about that. So 5 is basically the best I can do. Let us see. Yeah, 5 is the answer. Similarly, over here we can you can try this and convince yourself that 10 is the best answer. So all the points can possibly be, all the cats can be actually fed. That is what this says. Okay. Now, how to solve this problem? These are kind of intervals. So I can say that, hey, from the left, you can sort the intervals from the left. So the leftmost point, if the leftmost rectangle would have had the leftmost point alone, the other cats would start after this, let's say. We could have directly given this to this particular cat. Not in all the situations, but basically, we can have this kind of a strategy that as we move ahead, at every point, we will basically store that, okay, if I take this point, what is the best answer? We have seen, I've actually discussed this particular DP approach in some of my previous videos. I've discussed a video, I think that was blocking elements. And after that, I discussed another video on dynamic programming, again from a different Codeforces contest, if I'm not wrong. In both of them, I've actually shared how you can choose that strategy that, okay, an element, I have 2 options, whether I can choose it or I will not choose it. So for each of these points, you have 2 options. Now, what is the relationship? If I say that I'll choose this point, then I cannot choose this point. Why? If I say I have 2 options about this, I may choose or I may not choose. If I choose this point, I cannot choose any point up to here. I can choose points only up to here. So somewhere choosing this 7 means there are, this cat is going to see cannot choose 7, so no problem. This cat says you cannot choose anything over here. So some way starting here, these points get blocked and I am interested only in these points, whatever best I can get from there. I'm interested in only whatever best I can get from there. Similarly, let us see. One other observation that I get is, if I choose, let's say, this 12, what am I basically saying? I can choose up to this one. Up to this one I can choose whatever I want, but here I cannot choose anything because that green cat and this green, over there, that green cat covers this. Similarly, if I choose this 4, it basically says these I cannot take. Up to here I cannot take anything, before this I can take something. So somewhere, if we choose a certain, I, what does that mean? That if this I is a part of some LA to RA, let's say LB to RB and LC to RC, let's say that this I is a part of this, then what can I say? I can say that, hey, then before all of these, so you need to, you can only choose points, other points before I must, other points, let's say X, before I must follow, can I say X less than LA, X less than LB, X less than LC? All of them, they must follow all of them. Why? Because each of them states this: if you are choosing I, that means you cannot choose anything else within me. So I definitely have to choose things before these boundaries, before LA, LB, LC, which means my point X has to be less than the min of LA, LB, LC. And what will I choose? Can I say that, okay, we have discussed the DP formulation in those videos. Please take a look at those videos that were linked at that time. So when I first mentioned it, I've attached the link over there. Please check those videos. What I'm basically saying is, if we define it in this way, DPI basically is that if I choose I, what is the best value? If I choose I, what is the best value? Can I say it is nothing but at I, whatever points are there, let's say at I, the number of points is PTSI. So it will be PTSI plus the maximum you can get, the answer you can get up to from the first point up to the minimum of LA, LB, LC minus 1. Correct? Can I say that if I choose this 11, and up to here, whatever is the best, I will take that separately. I will add this impact of 11 over here. 11 feeds 2 cats. So I will take those 2 cats. From here, I will get 3 cats. So 3 cats from here, 2 cats over here. In that way, I will get 5 cats. So basically, this is my formulation. The DPI is basically, DPI is basically the maximum number of cats that can be fed in 0 to I. Okay, that lies somewhere in 0 to I, using points using points 1 to I, using some of the points 1 to I, using some of the points 1 to I, and mandatorily using I, point I. So what am I saying? That point I must be used, and up to I you can use any points. That is the, and here we will store the maximum number of cats. Now what can we say? This DP formulation is basically the number of cats covered in I. So I can say it's the number of cats covered in I. So number of cats covered in I plus the maximum of dpj such that j is less than the minimum of all the L of x, where xth cat shares is fed at point I, something like this. So basically, for all the j's up to that point, up to this j, or in this -1, basically over here I am up to there I am basically finding out the maximum. So can you see, this is a straightforward DP implementation. Of course, during a live contest, I am not claiming that this is that straightforward, but in this way you can basically solve this problem. Now, how do we find this maximum? This is the time, I think, let us take a look at what Tourist has done. So, Tourist, the submissions show that from around in 7 minutes he has submitted this problem. I'm pretty sure this is not his best, but let us take a look what he has done. So, all the L and R values have been taken. These are the inputs up to here. Now, he has done an interesting thing. This is a common technique. It's interesting how he has used it over here. This is a very common technique. So whenever you have to find that, hey, basically this thing, when you have to find this cat psi, how do you find the number of cats at every point? Number of cats that are important at every point. How many cats are belonging to the situation at every point? So for that, we can take this. We can say, okay, let us take this diagram. Sorry, let us take this diagram. Yeah. Now we have these points. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. After that, there is no sense of putting any points because there are no cats. So up to 13. Okay. Let us see. At 1, there is no cat. At 2, at 2, at 2 cat, let's number them maybe. This is cat 1, let us number according to what is given. 210, 3524, 35 is second one, 24 is third one. 77812, 77812, 11. If I go there, yeah, what do I have? The first point, this is where cats 1 and 3 will enter. Cats 1 and 3 will enter. Cat 1 and cat 3. They are entering the picture. At point 2, somewhere if I maintain an array, zero, 1, let's say only from 1, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, something like this, yeah. Now, at 1, 2 cats are entering. If I mark 2 over here, let's mark 2 over here. At 2, what is happening? At 2, okay, at 1 nothing is entering, at 2 they are entering. So sorry for the mistake. At 2 they are entering. Cat 1 and cat 3. At 2 they are entering. So I'll mark it as 2 at 2. Now at 3, cat 3 is cat 2 is entering. So now another cat is entering. I will mark this as 1. There is one cat entering. Then what else? Now for these cats, I'll do this, that okay, this guy, cat 1, let me do it from the beginning. Cat 1 is entering at 2 and leaving at 11. 11 onwards, it won't be there. So we can say, okay, put 1 due to this over here and minus 1 due to this over here. Next, for 3, 3 is entering at 2 and leaving at 5. 5 onwards, 3 won't be there. So entering at 2 means at 2 now we have 2 cats who are entering and leaving at 5. So at 5 I'll have minus 1. Now for this cat that enters at 3, cat number 2, starts at 3, leaves from 6. So at 3 we will have a 1 and at 6 we'll have a minus 1. Next, at 4 we have a 7. Now fourth cat basically enters and leaves at 7, means enters at 7, leaves from 8. From 8 onwards we will not have cat 4. 7 we are having a plus 1, 8 we are having a minus 1. Next, this fifth cat enters at 8, from 13 it is not there. So at 8 it has entered, so minus 1 plus 1, I can say this will turn it to 0. At 8, I'm adding 1 to this, so now it will become 0. And it's living at 13, so at 13 I'll have minus 1. Similarly over here 11 and living at 12. So at 11, once again it becomes 0. And at 12 I'll have minus 1. What does this give me? At each position it gives me number of cats entered minus number of cats left. If I know how many cats existed up to this position, can I say number of cats up at this position will be this number plus 2? Can I say? Up to here, if I know whatever is, let's say up to at position 5, I know that over there x cats are there. Then at position 6, can I say 1 cat less will be there, which means x minus 1 will be there. That is exactly what this is based on. So we can get the number of cats at every instant, at every time instant through this technique. This is a very good technique which tourist has used in his code. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. So initially it starts with 0. Then I'm going to add 0 plus 2 is 2. Then 2 plus next one is 1 is 3. Then 3 plus nothing, there is 0. So 3 plus 0 is 3. Then 3 minus 1 is 2. That means at 5th position 2 cats are covered. At 4th position 3 cats are covered. Can we check that? At 4th position 3 cats are covered. At 5th position 2 cats are covered. Can you see? So this is exactly what tourist has done over there. And it's quite a standard technique to be actually done over here. Because at every position, if I get the number of cats, I can directly use in this particular expression. That the best answer at I basically will be number of cats covered by I plus this thing. So yeah, this is a good thing. First of all, we are obtaining this cat sign through this array. This is basically our cat sign. Now, similar thing, 2 minus 1, 1, and so on. I'll be doing this 1 plus 1, 2, 2 plus 0, 2, 2 plus 0, 2, 2 plus 0, 2, 2 plus 0, 2, 2 minus 1, 1, 1 minus 1, 0, 0, 0. Yeah, this should be correct. Now, In this way, we have got cats 1. That is good. Now let us continue with today's solution. He has done exactly this. B of I plus 1 plus equals to bi. In this way, he is taking that prefix sum, and that prefix sum actually gives us the number of cats at any position. Next, at. He creates a vector at, and what is he doing? He is adding I and tilde I. What is this? This is a very interesting programming technique and definitely gives us a mathematical impression. This particular thing could have been done in different ways, but first let me tell you what does this mean. It basically tells that for every cat, add the left position of the cat at the left index. So in some data structure, go to li and add that, okay, at li, at this particular point, ith cat is entering. And at ri plus 1, from here, ith cat is discontinuing. We will push tilde I. What is tilde I? Tilde I basically is the ones complement of I. What is the significance? Basically, whatever bits are set in I, those will become unset. Whatever bits are unset in I, those will become set. So if my I is basically a positive integer, then we know that its leftmost bit, its sign bit, its sign bit, that is the leftmost bit, is equal to 0. The moment I take a ones complement, I'll get tilde I, which will have one unsigned bit, and one unsigned bit basically would mean that it is lying in the range minus 2 to the power 31 to 2 to the power 31 minus 1, or if it is long, then minus 2 to the power 63, 2 to the power 63 minus 1, minus 2 to the power so if it is negative, that means it is basically lying from here to minus 1, There are exactly 2 to the power 31 numbers over here and 2 to the power 63 numbers over here, which are the 2 to the power 31 possible ways, or 2 to the power 63 possible ways of filling the other gaps, keeping the leftmost integer 1. So yeah, your answer, your ones complement will lie in this range, which means that this will be negative. This will definitely be negative. So I, we know, is positive, and the reason why, again, my anticipations, the reason why he did this is that it sets a clear distinction between positive and negative. Putting I basically means it is positive, so it is the entry point. Tilde I will be negative. If I do another tilde, if I basically say, okay, tilde of tilde I, this will give me I. And that is exactly what he probably would have wanted here. That, okay, if I get a negative number, I'll take a tilde and I'll get the positive number. So let us see what has he done. At li, he has pushed I. At ri plus 1, he has pushed tilde I. So let us complete this. This is actually our at L. At 2, 1 is entering and 1 is leaving from 11 onwards. So at 11, we will have tilde 1. Similarly for 2, entering at 3 and going up to 5 means 6, we will have tilde 2. 3, 2 to 4. So at 5, we have tilde 3. Fourth cat, 7 to 7. So 7, 4 and 8 will have tilde 4. Then we have 8 to 12 as the fifth cat. So 8 and 13. 8 and 13 will have 5 and tilde 5. Then 11 and 12 will have 6 and tilde 6. 11 and 12 will have 6 and tilde 6. This is the significance. Now, I know on going to every position, if I ask, hey, what happened at u? I will see tilde 3, this is negative, so I can do tilde of this negative number to get 3. That means 3 has left. Negative means there is some element has left, so I can do. Now, we could have stored different things. We could have actually stored it in two different arrays, who entered and who left. But this actually gives us a very good mathematical vibe. In a single array, the entries, exits both have been stored using a very interesting knowledge of the bitwise representations. And bitwise manipulations, as I've shared in one of my previous videos, is my favorite. So this definitely makes me a fan of Tourist. This is definitely once again a very small thing. We should never judge a programmer like Tourist from any of these simple things, but these are things we definitely can learn from. Next, he has used a Fenwick tree. Okay, Fenwick tree makes the situation very interesting. Going back, what did we discuss? We need the maximum of dpj. I will show if by the end of the solution if that is exactly what he did. But if we need the maximum of dpj in a certain range, finding the maximum of the range, especially it is basically this range basically is, we can say something like this, from 0 to min of lx minus 1. This is the range. So in this range, if we want to find out the maximum or the minimum, if we have to find out the maximum or the minimum, whatever, if we have to find out, if we have to, let's say, update at points, something like point update, at any ith point, basically we want to update it, and we want to query ranges. We want to do range queries. A range query not of any arbitrary form, specifically of this form, that the start, which is definitely 0, up to any j. If I basically want this, or up to any I or any j, whatever, if I want this, a good data structure over there is Fenwick tree. Or binary index tree. So I'll not go very detailed into very depth of what exactly, how exactly it works, etc. But what is a property of this kind of a tree? I'll share in short. So when we say that, hey, update a certain point I, now after that, if I query for I plus 2 or I plus 5, using bitwise calculations, what will this do? This tree basically has the property to check all the relevant positions and find out what is the maximum at those positions. What is the maximum, and also for some other properties we can use it. So what is done is, basically using I, when I am updating this point I, it uses this I to update many other points. It uses this I to actually update many other points. What are those points? We usually express in this way. So if I open this solution, it will tell you that when we want to update a point, for example this, we want to modify. At I, we want this value dp to be placed. So let us see what is he doing. At modify, he is basically saying, go to these positions and apply the same operation. Go to these positions and apply the same operation. X or x plus 1. That is, we will update at I, then we will go to I or I plus 1. This we will store in I, we will do there. Then again this I we will take and we will go to the position I or I plus 1 and so on. How long shall we go? Definitely you can understand that I plus 1 is definitely greater than I, so definitely this value will keep on increasing. From I to here it will keep on increasing. So how long shall we go? As long as it is less than n. This is a strategy of basically updating some nodes, updating some points. And then while we want to get, if we want to get at a point x, basically up to a point x, what is the maximum? This is a strategy that, okay, take the value at x and then go to a previous value. This is what gives the previous value, x and x plus 1 minus 1. So x and x plus 1 definitely will give a value less than equal to x. We know this. And minus 1 will take us before that. So definitely the value of x will keep on decreasing. We will take this up to 0. How this will cover all possibilities, etc., is a much bigger session. So somehow I will leave this with some summaries that for this situation, this is what we want. And Fenwick tree is such a structure which these computer programmers who are very awesome with mathematical stuff, they frequently use these data structures because they understand the mathematics to the very depth, to the letter. So by this, what happens that I'm not in a position to comment on whether he actually implemented this during the contest or not. I believe he hasn't. I believe he has used some template from somewhere. But the important part is that this is also a very well written thing. There are two functions, modify and get. This is a very easy code, or very not an easy but a very clean code. At any point of time, you can go and see what exactly it is doing, and you can do a dry run. And then he's just using these two functions, modify and get. So first of all, from the beginning, what is he doing? He is creating an object of Fenwick node. If we look at Fenwick, or if we look at node basically has this. It has an integer, so it stores that value, and it has this thing. It has overridden the plus operator. It has said, okay, whenever you say plus, it basically means max. So this is again something that good C++ programmers do use. I'm primarily a Java programmer, so I don't use much of these, but these are some good programming constructs. If you basically want to save your time not writing max and min, you can basically use these things. So plus equal to, this basically means that your plus operator is getting overridden. So what is happening over here? The moment we say that Fenwick x plus equals to v, what does this mean? That okay, take this value at x and take this value v. The maximum of these two values will go to Fenwick x. Fenwick x, what is this? Fenwick x basically is, so this is a vector of t. And what is this t? We have defined this t to be node. So it will follow this node's implementation of plus, because we are adding v. V is of type t, that is node, and Fenwick of x is again of type node. So we are adding one of node to another node. And what is the implementation of addition of node? It is maximum. So we are basically computing this maximum and storing it in this Fenwick of x. And then we are proceeding to this. By this Fenwick implementation, what happens? That if we want to do this operation, that at any point I want to update, and then I want to query the maximum up to a certain point. This is a very clean implementation. Can you see, given the template lies above, and you are accustomed to this template, what do you have to do? You basically have to say, okay, this is our algorithm. So it basically says, I'll go into the details of this in a moment, but he says that, okay, from is basically up to where I need the best answer. So over there it is saying that, okay, up to you, what is the best? Give me that. Fenwick tree gives the best. Whatever is up to there, it gives the value, dot a. A will store the value. Let us check how a stores the value. A over here. Fenwick of x plus equals to v. A is not getting exposed at least to that function. But over here we are basically saying a equals to max of these two. A and other dot a. That's it. Got it? So this plus operator basically leads to the operation on this a parameter. And so we are now taking out this a parameter, adding our bi, which is cat psi. We are adding the cat psi. So again, going back, this is our implementation. We had this cat psi. This is nothing but bi in tourist implementation, and this he is finding from the Fenwick tree by applying Fenwick dot get min of lx minus 1. And We will just focus on what he is doing. He is basically getting this value, adding this is dp, and this is where he is modifying the Fenwick tree. This is the only thing he is doing with Fenwick tree. He just defined a Fenwick tree and then got the value from here and then modified the Fenwick tree. How? Whatever dp value, whatever answer has been got, whatever dp value has been got at this position, he's saying that okay, at this position or up to this position, this is the best value. Update in the Fenwick tree because something else may require this. We already saw this, that dp actually depends on the previous dp values. So we have to store this dp value somewhere. So we are storing this in the Fenwick trees. This also we are storing in the Fenwick tree. So in the Fenwick tree, this is the storage, or this is the storage and this is the fetching. Just in 2 steps, the operation on the Fenwick tree is done. That tells us why he used Fenwick tree. Why he didn't use something else. What else could he have used? You can definitely use, instead of Fenwick tree, you could have definitely used segment trees. Segment trees in this case would have given you much more flexibility, which you wouldn't need. It gives you much more flexibility in this situation, but you don't need here. You don't need here. You don't need any range. You don't need any range. You need just that particular range. You need that only that particular range. If you need, if you suppose would have needed any range, let's say L to R. In L to R, what is the maximum? Then Fenwick tree would not help you. If you need the sum, then you can definitely do those kind of things. That up to R, what is the sum? Up to L minus 1, what is the sum? Fenwick tree would have helped you get that. I'll not go into those details, but for these kind of operations where inverse of a minimum is not possible, like minimum of 2 ranges, minimum of both will give something, and then from there I'll get the minimum of one of them, is that that is not possible. So Fenwick tree has been purposely used here because we only are dealing with prefixes. Because we are dealing with prefixes, Fenwick tree is a good choice over here, right? Okay, next let us complete this solution. For every element in ATI, check if you have LJ, s dot insert LJ. Basically, if j is greater than or equal to 0, that means this is an entry point. Then add the time of entry of j. We are adding into a multi-set. Why? We'll see that. But we are inserting that, and if j is negative, then we will say, okay, remove from the multi-set. So again, do a one's complement of j, then you get the real j, then find out what is the real j, that is what was the time in which j entered, and remove that from s. So whatever we entered here, we are actually removing over here later on, right? And we are iterating I in the positive order, so basically we are starting with 0th position, then 1st position, then 2nd position, and so on. Okay, what next? Next is from s.empty. If s is empty, then we will say up to the previous position, take the best value. That is what we are doing. From equals to I minus 1, previous position. From the previous position, we will take the best value of dp. If s is not empty, what will we say? Whatever is the minimum, starting point among the points that are in s, or whatever is the minimum starting time. We have just added integers, so whatever is the minimum starting time, that minus 1. So we have already discussed this. This is nothing but the minimum of Lx minus 1. So that's exactly what we are doing here. This is the minimum minus 1. We are finding the dp, and then we are computing the answer as the maximum of the dp till now. This is the answer. Great. So how could have we done this differently? First of all, there is this interesting use of a multi-set. Why multi-set? Because the same LJ may be entered by 2 different points. In 7 minutes, there are so many nitty-gritty that are being considered over here. This is definitely didactic. And as I mentioned, he definitely can code faster than this. And remember, in the 7 minutes, he has also read the problem. So yeah, that tells the kind of programmer definitely he is. Okay, now the next part is, we have discussed that okay, instead of Fenwick tree we can use segment tree. Can we do this in a simpler manner? Here I want to give one disclaimer. This is not a comparative analysis. I'm not definitely into any kind of judgment. This is just a bit of brainstorming from here. It will be a total foolishness, total stupidity for me to say, okay, it can be done differently and that probably could be better. Not at all. Because this is where tourist is. This is somewhere where I am. We are all average programmers who are trying to learn something from what these great programmers like tourist has done. So not at all any kind of comparison, but it's basically a bit of brainstorming. So segment trees we can use, but if we try to avoid it completely, over here we clearly know that there is this maximization function. But can I say that if your dp value basically, if your dp j minus 1, let's say your dp j minus 1, which is the best answer choosing j minus 1, dp j minus 1, which is the best answer choosing j minus 1, that is less than or that is greater than dpj. Okay, so this is a better answer. J minus 1 contains a better answer. Then can I say that j is of no use to us? This is of use to us. Always going forward, where whatever I asks, I will never ask for this one, should never ask for this one. It will ask for the maximum up to here maybe, and always this will beat this one. We use a similar technique in monotonic queues. We say if a bad answer is coming after this, then just ignore it, something like that. So over here, can I say that storing the maximum till now is always in our always uh, will be benefiting us? If I say I won't store, this is my dp, let's say this is my dp, let's say this is my dp, and I define dp1 of I as the maximum of dpj such that j belongs to 0 to I. So basically I'm taking the maximum. Can I say my dpi can be more easily formulated? If that is how I'm defining my dp1, then let me take this. This is my dpi. Instead of that, if I try to do dp1 of I, can I say that it will be cats of I plus the dp1 of main of lx minus 1, that's it. Can I say? So if I ignore the lesser values of dp, if I always consider the maximum till now, that is what I stored in dp1. What is dp1 of 0? Up to 0th point, it is 0. Nothing has been taken till now. So I have the base case. I have the recurrence relation. I don't need dp at all. I don't need this dp at all. Can I say this is a easier thing for me? And I don't need the maximum of dp values. I just need one dp value. What different did we do over here? The different thing that I basically did is store only the maximum value. Don't store so many different values because we don't have the point query. Fenwick tree would also help us only in those range queries. And I know that what ranges I'm concerned in. I know in those ranges basically if I store the max till now at every position, that helps in giving me that same value. So over here we can basically do just that. We can only store this and then it is done. We don't need the Fenwick trees. Now Does that mean that we have found a better solution than tourist? No, no, definitely not. Because tourist has used Fenwick Tree in just 2-3 lines. In 2-3 lines, if you can use such a complex data structure to your success, and you don't have to think in a complicated way or in a more carry forward way, if you can use some complex data structure like this to your advantage and keep on solving problems, nobody like me should dare to even say that it can be done without a Fenwick Tree or should be done without a Fenwick Tree. No, if you are comfortably doing it, you should be doing it. Did tourist not know that without a Fenwick Tree it cannot be done? Definitely he knew that there are 2-3 other ways of solving it. He did this because he is very well practiced at it. He knows he can do it very fast. I'm not going into whether he thought any other things or not, because I cannot think of those things. But this problem can be solved in many different ways. And over here, he has used Fenwick trees, and what we get is a very neat and tidy explanation, or very neat and tidy demonstration of using Fenwick trees to solve the problem. What next? He has used multiset, which is also a very intelligent use over here. Remembering all these values in Java, probably I have to use a tree map to store the frequency as well. But more or less the idea would remain the same. Now, can we do it without using this? Without using this, can it be done? Without using the multi-set? If I look at the problem, maybe an example. So when I say 2, 10, I know that for these points 2 is going to be one of my blockers. If I choose any of these points, 2 will be one of my blockers. If I'm coming from the back, it is possible to actually ignore a map. If we just say that, hey, I mean, if we keep on storing this somewhere like this, then, I mean, if we keep on iterating from the back, let's say we have this kind of a structure. Zero, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. Yeah. If I say over here 2 to 10, let's say 2 to 10, and another one is there, which is 2 to 3, or 3 to 5 here. Let's say only 3 to 5. 3 to 5. What can I say? The moment, let's say I'm iterating from the right. The moment I have this 10, I can say, okay, from here, if you take anything, this 2 is basically going to stay at your watch. I can keep on storing this 2 over here. Over here, I can keep on storing this 2 till the very beginning. I can say, okay, before 2 you cannot take anything, something like this. Over here I will not have, but over there I'll have. For this 3 to 5 also I'll have similar thing, that before 3 you cannot take anything. We will store the minimum one because that is what matters to us. Let me take a smaller one. Let's say 1 to 4. I can say, okay, over here I will say before 1 you have to choose, right? Similarly, if I choose something over here, let's say in this part, what can I say? That yeah, you have to choose before 10. So 10, 10. In this way, if I iterate from the right, I can keep track of these things. Now, for each range, for each bracket, do I have to update all of them? No, I can do an optimization there, just like the optimization we did over here. We will first take all this +1, -1, then we will accumulate into this. The same thing I could have done actually. Now, would that reduce my time during the contest? No, but this is one possibility. In other words, is this a bad approach of not having followed that? Definitely not, because once again, probably coding this was the fastest way. If we give time, tourists can find out 20, 30 different solutions for every one different solution that we are finding. But the thing to learn over here is he's choosing the best approach. And in these kind of contests, you can actually solve in many different ways. We actually established that we don't need the Fenwick tree, we don't need the segment tree, we just need the DP array. We don't even need the multi-set. If we think a bit, I think we'll be able to reach solutions without the multi-set. With this array, now we don't need multi-set. But what is the idea of data structures? Use such data structures which can solve your problem in the simplest possible way. And that is exactly what he has done. So this is a good problem and it was interesting. I hope you enjoyed seeing the solution of tourist in this particular problem. Now we will finally discuss the last problem, problem G. Problem G basically says that there are n platforms connected by m passages. I'll just share some key highlights over here. I won't go into the very details of this. Already it has been a very long video, and there are some really good algorithms being used over here. I'll throw light on some of them, and then you can sit at your leisure time and actually try to solve this problem. So between these different platforms we have passages. So there are n platforms and they are connected by m passages. Each are at some level, and so the ith one is at level li, and at with every step, with every second, it rises by si. Its level changes by li plus si mod h. So they can go maximum up to h minus 1, and this is how the levels are changing. Now, to move to platform J, they have to be connected by the passage, and their levels have to be the same, namely Li equal to Lj. So, quickly understanding the problem, basically, from I, if I have to move to a J, what is important? There should be a passage from I to J. These passages are given. These are like edges of this graph. So there are n nodes and there are m edges. So these are like the m edges. This is one edge, so the edge needs to be present for you to directly move. Plus, they need to be at the same level. So at this point of time, Li must be equal to Lj. What else? Yeah, that's it. Now, as long as they cannot move, they have to wait. At every second, these levels will change by this Si. So at this point, whatever point, basically, after t seconds, it will be Li plus t into Si multiplied by, modulo h, and this one will be Lj plus t into Sj modulo h. Got it? Okay. And if these are same, then at this time t they can move. Now you cannot move from from I to a certain j and a certain k at the same time. It's like it's a person who is moving from one point to another. In 1 second, you can only move from one point to another. You can't hop to 3 points together. Okay. Now you have to find the minimum number of steps needed to get from I to n. Steps basically means at each step the levels of all platform change. So that step, number of seconds basically elapsed before you reach the platform n. So the source is known, the destination is known. It's a graph question. What comes to mind? Definitely, don't hesitate. It's definitely one of those given source, single destination problems. So you can solve shortest path problems or shortest path of single source, shortest path, We have a set of algorithms. We have BFS. We have, we don't have DFS. We can't use DFS. We have Dijkstra. We have other algorithms as well. Um, Floyd Warshall and many others. So Dijkstra is one algorithm which we say is very suitable for single source, single destination. So now how can we use Dijkstra over here? What we know is that at every point it changes. At every point, at every step we can say, or at every second, the the set of j's to which we can go from a certain I changes. Now the question is, from a certain I, which j should I go to? Here the same property of Dijkstra should hold. If you can go from a certain I to a certain j at the very beginning, I mean before the other j's, you should go over there. So you should keep in mind what are the j's, what is the context, or what is the thing you should check. You should check that there is an edge and their else are same. So among those where you have edges, you will have some j1, j2, j3. So the idea is somewhat like this, that from I to j1, it can take a lot of steps. You can't simulate every step, you can't do that. So you have to find out, okay, what is the t1 number of steps needed, what is the t2 number of steps needed, what is the t3 number of steps needed, and then find out the minimum to cover that. Find out the minimum to cover that. In fact, take all of them. A good approach, or the better approach, would be to take all of them. That J1 I can reach in time T1, J2 in time T2, and J3 in time T3. And then with all of them, you can start seeing, okay, through what you can reach the final destination. I think that's what Dijkstra is actually doing. The sequence is driven by which one is the minimum, but otherwise Dijkstra considers all of them as the intermediary points. Okay, so now the big question is that, okay, from I to j, in what time t1 can I reach? Let us, without wasting any time, go to the solution of tourist. In 9 minutes, it seems that he had solved this problem. There is definitely a good level problem. There are 389 people who have solved it, including these unofficial participants like tourist. So definitely a good level problem. Let us try to see what he has done. It's a big code. Considering the kind of codes we have been seeing for tourists, it's a big code. Let us see. Up to here, it's the input. He's forming the adjacency list kind of thing over here, which is fine. Next. More or less that kind of thing he is doing, as we discussed. A distance of the points. N is at distance infinity. Here by distance, what do we mean? Logically, up to now we can understand it means the number of seconds that this point is away. So it's basically saying that all the points are at infinite distance and zeroth point is at zero distance. That is, zeroth point is already reached. That is the source. Great. He has already done minus minus on all the points. Minus minus x minus minus y, which means that the points are zero indexed for us. Awesome. Next. Q.emplace dist 0, 0. He is adding this in the priority queue, saying that so this is the priority queue, pair int 64 int, over there a vector basically is okay, so first element is the pair. Let us understand this. First element is a pair, second element is a vector of a pair, okay, with a comparator, if I am not wrong. No, For this priority queue, this is the comparator. So the greater one, okay, greater pair int 64 int. Let us see how this is basically happening. Dist 0 0, dist 2 2. So basically it is telling that okay, 0 for 0 0 is present at distance 0. If we look at this line, we know that okay, 2 is present at distance 2. So somewhere that is what is happening over here. Then priority queue is okay, this reminds me something. Now I can make sense of it. So a priority queue is actually in C++ it acts like a max queue. It acts like a max priority queue. Over here, or max heap. Over here we want the minimum value. That's why he is reverting it over here so that we get a min heap, because we need the minimum distance first. That is how the sequence actually makes sense. We need the minimum, so he has actually reverted it. He's saying that whichever is greater, make that come before. So because it behaves like a max heap, he is now reverting the nature by saying that okay, I want the greater one first, something like that. That reverts the thing finally, and so it becomes a min heap. Okay, next. What next? While queue is not empty, we will do this. What are we doing? This is basic Dijkstra. For Dijkstra, you can actually look up Dijkstra algorithm. You can follow CP algorithms. It's a fair explanation. Finding shortest path on graphs. You can follow this. You have the code also. You have a proof. So here also, if you want to prove how it will work that way, so you can use this proof and try to get that proof. Basically, this is also this is exactly the kind of thing we are doing over there. Tourist is actually doing over there. So it's using a priority queue. Let us see if he is using a priority queue. Uh, Auto adjacent this store path. Um, for edge in this p dot assign. What is this p? This is a vector. D dot assign vector. D is a vector. Okay, fine. We can look at it later, but here or somewhere else, definitely you should be able to find a priority queue solution. That is quite central to this algorithm. Anyway, the way it is given here, that way also you can figure out. We quickly see I to n, and then auto dv. How are we choosing this? Auto edge adj of v. Am I looking at the right thing? Dijkstra algorithm, single source shortest path. Okay, you can take a look at this. You can learn it. You can see how they are actually finding it, what order they are processing it. Okay. Let us proceed to our solution. We want to get in that order. Now, expected. What is this expected? Q dot top dot first. I equals to Q dot top dot second. Dist I is not equal to expected. Expected basically means over here, the pair that I am finding from my queue. Why I am picking this pair? Because this is my current pair from where, current point from where I'll be visiting some other point. So it's something like in queue, I'll be storing these points. Maybe dist of 3, 3, dist of 4, 4. And now I am saying that if for this 3, this dist 3 is obsolete. Maybe the distance of 3 has changed later on. So what should we do? We should not consider this dist 3 any longer. So that is exactly what Tourist has done over here. This is also a very common thing in Dijkstra implementation or somewhere this should come. In some other algorithms, like I think Prim's algorithm, you should be able to get that. This use of priority queues. So if dist is not equal to expected, that means this is not an important pair. We can discuss this in detail. Why this comes is a very interesting case. for let's say we find two different ways to reach J1. Once we are reaching from I, another time we are reaching through J2. So then which particular, let's say the second part is actually a shorter one. If the second path is a shorter one, we will take this path, and then if this one comes to the top, I will neglect this one. I'll say, okay, this one I'm not going to take. Even if this comes later, I will say, okay, this one I'm not going to take. So I'm going to check with the latest distance. If the latest distance does not match with that distance which is stored, I will ignore that distance. Okay, so this is exactly what is happening. This display, we can make much sense in a short while when we look at the entire code. What is he doing? For this I, he is taking all the vertices to which we can go from I. And for each of these vertices, we will say, okay, what is our difference and what is our delta at every step? What is our difference that we can go, what that we need to go, and what is the delta that we have to go? And using these two things, we are processing some kind of a Diophantine function, or we are solving a Diophantine equation. This is a real advanced thing. You can actually search it in your so yeah, you have it here. Linear Diophantine equation in CP algorithms. You can read it up. So it basically helps solve this kind of equations. Helps you in finding x and y, where x and y are unknowns, a, b, and c are knowns. So he's actually solving a Diophantine equation. By that, what is he getting? He is getting that, okay, how many times you need to shift, in what time you will reach that position TO. If that is better than your previous distance up to TO, you will update the distance and you will push the new distance into the queue. You will not remove the other distances from the queue. So this particular part is the Diophantine, and this part is also an extension of that. Let me discuss a bit about Diophantine, but before that, what are we doing over here? We are basically storing this dist. Now we are adding this dist to for maybe multiple times for the same TO. For the same TO, we are we are adding this multiple times for the same TO. Whenever distance is improving, we are adding this. That is why we had this check over here. That if it is not equal to expected, then continue. How do we know what is expected? Q.top.first. This is basically what we are adding over here. And what is this dist of I? We are storing this dist of 2 over here. So these two will be mapped that, hey, if this is matching, that means this is to be considered. Otherwise, this need not be considered, something like that. Now, Diophantine, let me share a bit of thing over here. So this is I, this is J, Li, Lj, Li plus Si into T minus Lj plus Sj, or we can say this modulo this Sj into T mod H. This is what is given. That is, they have the same modulo with respect to H, right? This is how we mathematically write it, which means Li plus Si into T minus Lj minus Sj into T whole modulus H equal to 0, which means this is equal to some K times H, right? Or H times K, some H times K it has to be, which means I can say Li minus Lj, this we can take separately. Let's focus on the right hand side. Hk plus Sj minus Si multiplied by T is equal to Li minus Lj. Can we say this? And this, my dear friends, is exactly what is Diophantine equation. Ax plus by equal to c. If I write over here Ax plus by equal to c. A is a known parameter H. K is unknown. We have to find out K, right? We don't know K. We don't know T. So we have to find out. B we know already. That is this thing. C is already known. So this is unknown. This is unknown. We have to find this out. The rest three are known. So it comes in basically this format where X and Y are unknown. So this is your linear Diophantine equation. Got it? So tourist has so quickly observed that this is a linear Diophantine equation, and then he used his expertise in that. He has basically figured out what will be this X and Y. He has basically figured out what will be this X and Y. We can find out, as you will see over here, we can find out one solution, we can find out all solutions, we can find out solution with minimum value of X and Y. What do we need over here? Here we need whichever has the minimum Y, whichever has the minimum Y. And also there are some constraints like whether the H can be positive or whether it can be negative or not. Those things we have to actually see. So it's not, I mean, the solution doesn't end over here. You can see he basically called this Diophantine with what? He basically called it with delta, H and diff, and then these three parameters X, Y and G. X, Y and G. Now with these, what is he doing? He is basically saying H divided by G is the shift. H divided by G is a kind of shift. We will look into that. But this X he is basically adding some shifts, removing some shifts, and then he is assigning this to new dist as X plus 1. What does this mean? This means that X plus 1 or X basically is the time interval after which they will meet. So somehow X is being passed, X variable is storing nothing, but it is being passed by reference actually. If you see this, X is passed by reference over here, X, Y and G. X is passed by reference over here. Now I think this is some template which has been taken, because if we look over here, delta, H and diff, if you remember this order, delta, that is the whole delta between those two, what is the difference? That delta can be 0, but we know that H cannot be 0. So this is the usual structure of this Diophantine equation, how that is solved. B I don't think can be 0. In our problem I don't think B can be 0. Sorry, in G I don't think that H can be 1. Can it be? Oh, H can be 1. That is interesting. That is interesting. So even that case has been considered, that if H is 1 then all are 0. And in that case, right, that case, yeah. Instead of making a case separately, what he has done is he has used that Diophantine formula to actually even pass for that. So we can say yes, if everything is 0, then return true. If everything is 0 but this C is not 0, what is this C? This C is the difference. And what is this difference? This difference is the main difference between the levels. Delta is the difference between, the difference by which they can overcome that gap. But diff is the actual difference. If the diff is non-zero, then it is going to return false if everything else is 0. So in this way you can understand most of this. It uses extended Euclidean algorithm. Why? Because how they're coming closer, again, let's say the difference was 6. Let's say the difference was 6 between the two, or let's say H is equal to 6. And if their delta is equal to 2, at every step the delta is 2, and their difference, the Li minus Lj, is equal to 1, can I say this del equal to 2 will ensure that they will always have even difference between them? because this h is even. If this h would have been odd, then we would have odd difference. But since this h is even, we will have even difference only. This is the problem, or rather, this is the reason why GCD becomes important. If they have a common factor, if they have some GCD, and if this delta does not divide that, or the G does not divide this difference, then this is again unsolvable. So those issues will come up. This is where that condition is coming, that if C modulus G is not equal to 0, then return false. So again, this is a problem which I would have really faced difficulty in trying in a live contest. I'm not trying to pass any commentary on what Tourist has done over here. It is just trying to understand how a complex algorithm has been used and to gain something from the thing. So he has identified very quickly that it falls in this linear Diophantine equation, and then he has used his expertise to figure out those things. He has figured out that x, which is the distance it has to go, and now in Diophantine equation we can find out the answer with the minimum y or those things. What instead he has done is he has first found out a y. In this case, it is the y for us, right? The t over here. So he has found out that, which is the x in his case. He has found out that x, and then what is he saying? He is saying that if the x is less than the distance, that cannot happen, because from distance I, it can only be greater, right? So it cannot be so. So x will be that point in time when you know when basically probably x has been calculated from the very beginning, from t equal to 0, and now we are checking, okay, from the time when the control has come to I, how much more time do we need, how much more time do we need. So that can be calculated using this. What is he doing? He is basically moving in multiples of shift. That is it. This can be understood from here. He is moving forward in multiples of shift. He is basically saying, okay, whatever is the difference up to dist I, take that difference by shift plus 1, multiply by shift. This plus 1 indicates that now it will be located in the multiple of shift after dist I. So basically, after that step, if our, what was our variable, x and dist I, if our x is over here and dist I is over here, we are basically taking jumps in G, right? In shift, right? In shift, I'm calling it SH, again another SH, again another SH, something like this. So in the first SH, we will stop over here. This is what we are doing, right? And next, in the next one, what are we doing? Bringing it closer. If it is far away, we are bringing it closer. X minus dist I, divide by shift, multiply by shift, something like this. That if your x is located here, then you are basically subtracting. You are bringing back by SH, again by SH, again by SH to this last place. So this again is required. It basically tells you what is the minimum time you need to go to the jth index. For every j we will do this, and if you cannot go, then this will return false and you will not add it. That is it. There's a difficult problem, but I hope you have got some percentage of it, and this encourages you to actually try these difficult problems and not just fly away from just seeing it as some unknown topic or complicated topic. So anyway, I hope you like this session. This was quite a daring attempt to uh, try to actually take a live session with tourist solution here. Um, but I hope you got something from the session. Let me know if you would like to see something similar with some differences. If you would like to discuss some other contests that you found interesting, I'd be happy to discuss. So yeah, please like, share, subscribe if you find the video informative, and let me know if you have any doubts, queries about these problems that I discussed or any other problems. Thank you, take care, keep coding.